In this video, we're going to look at an interesting and useful connection between the formula for the Wronskian and the coefficient functions in the differential equation. For this topic, it will be useful to have our differential equation in normal form. At this point, we're only considering second-order linear homogeneous differential equations. We can always put a differential equation like that in normal form if we need to, just by dividing through by whatever the coefficient function of y double prime is, if necessary. The connection that we need is in a formula due to Abel's formula for the Wronskian, stated here. If y1 and y2 are any two solutions of your dE in normal form and W is their Wronskian, then W is always equal to this expression in terms of big P of x, the coefficient of y prime in the dE in normal form. The proof is actually fairly straightforward, and it's a nice application of things we were doing in the previous chapter. So we'll go ahead and look at the proof of Abel's formula before going on. The first thing we have here is just reminding you what the Wronskian is. It's defined to be that expression, just that 2 by 2 determinant. And the first step in this proof is just to take the derivative of that, which is what's happening here. We use the product rule twice, so we get two terms when we use the product rule for the derivative of the first term in the previous line, and then we get two more terms when we use the product rule for the derivative of the second part in the previous line. And then the y1 prime and y2 prime cancel out, which just leaves that expression for the derivative of the Wronskian. At that point, the idea is to replace each of the expressions for the second derivative by equivalent expressions from the differential equation. So since y2 double prime is, since y2 is a solution of the differential equation star up above, y2 double prime must be equal to minus p y2 prime minus q y2. And similarly, we're assuming y1 is a solution of that same equation, so y1 double prime must be equal to minus p y1 prime minus q y1. So we can substitute in those expressions from our differential equation, and then we see that the terms involving q cancel out. We have minus q y1 y2 from the first part and plus q y1 y2 from the second part, so those terms cancel out, and all we're left with is minus p y1 y2 prime minus y2 y1 prime, and we see all we're left with is minus big P times the Wronskian. So that gives us this first order differential equation for the Wronskian, and we know how to solve first order DEs from our work in the previous chapter. The integrating factor is just e to the integral big P of x dx. We do the usual thing with that, multiply both sides of the differential equation by our integrating factor, and then once we do that, this expression, the left side of this equation, just becomes the derivative of a product as usual. So we integrate both sides of that, and we just get that product for the integral of the left-hand side, and the antiderivative of 0 is a constant, and then we can solve that for w, and we get the desired expression for Abel's formula for the Wronskian. This probably seems a little bit theoretical here, and maybe it is, but this gives you a very useful way to find a second linearly independent solution when you need one. That's going to be the main application of this formula, which we'll start looking at on the next slide. Before we do that, we'll look at just a couple quick examples to get hopefully more comfortable with Abel's formula. In example 1, we had y double prime minus y prime equals 0 was our differential equation. So which is already in normal form. So reading off the coefficient of y prime is big P of x is -1. Plugging that into Abel's formula and integrating, we get that expression for the Wronskian, which agrees with what we had for the Wronskian in example 4c. Similarly, in example 2, we had this differential equation. The coefficient of y prime is 0 in that equation. So plugging that in, plugging in 0 for big P into Abel's formula, we get the Wronskian as a constant times e to the 0, or just a constant. And this agrees with what we came up with for the Wronskian in example 4b. So hopefully those examples will help you get a little more comfortable with Abel's formula, how it works, and what it's telling us. The main reason we're interested in this is this theorem. It's really just an identity, but it's a very useful way to find a second linearly independent solution, y2, when we have one known solution, y1. If you just think about the derivative of the ratio y2 over y1 and just calculate that using the quotient rule in the usual way from calculus, you get the denominator squared, y1 squared, which we're thinking of as being a known thing. And in the numerator, using the usual quotient rule formula, we get y1, y2 prime minus y2, y1 prime, but that's just the Wronskian. So that means that the derivative of y2 over y1 is just equal to the Wronskian over y1 squared. And here we're thinking of y1 as being a known solution and the Wronskian being known from Abel's formula in a typical application of this identity. So the way we're going to use this, and I'm going to ask the viewer to try it and before going on to the next video. So the way you would use this in a typical application of this information, you would have the Wronskian would be a known thing, y1 would be a known thing, so therefore the Wronskian over y1 squared would be a known thing. According to the identity which we just observed above, then y2 over y1 prime would be equal to the Wronskian over y1 squared. So y2 over y1 would just be the integral or antiderivative of that. So if we can do that integration, that will give us a known expression for the ratio y2 over y1, and then we just solve that for y2 to get our linearly independent solution. So that's the procedure in terms of applying Abel's formula and the identity in the theorem up above. So I'm going to ask you to try this before going on to the next video. Use a given differential equation and one given solution to find a second linearly independent solution. Now, the first two examples, example 7a and b, we already completely solved the problem, but the idea here is let's pretend we don't already have two solutions. Let's pretend maybe we were able to guess one solution, and then we're looking for a second linearly independent solution. This will illustrate how we can use that identity and that theorem to find a second linearly independent solution when we need one. So here's the first example that I'll ask you to try. Given differential equation and one solution y1, can you use that procedure to find a second linearly independent solution? Here's a second example I'll ask you to try. Y double prime minus k squared y equals 0. And suppose we knew y1 of x was e to the kx. Suppose we knew that was one solution and we were looking for a second linearly independent solution to that dE. And then finally, here's a dE that we haven't worked with much yet, but it's one that will come up quite often in this chapter and in applications. Y double prime plus y equals 0. Suppose it were possible somehow to guess that y1 of x is cosine x is a solution of that differential equation, and we are looking for a second linearly independent solution. How could we do that? So I'll ask the viewer to try and go through this three-step process. Again, use Abel's formula for the Wronskian for step 1, and then use that identity to find a second linearly independent solution if you have one solution. We'll always leave out irrelevant constants with this method. All we're trying to do is come up with a second linearly independent solution of the simplest possible form. So we're going to be leaving out a lot of constants here with all of this. So give that a try.